Good morning all of you. Today we shall study about the combination of cells. You are all aware that we combine the cells in simple circuits. In your torchlight is a common combination of cells that we are using, where you are having two cells being combined, and I am sure you are aware it is a combination of cells that is being combined in series. We can have the combination of cells either in series or in parallel, or we can have a mixed combination of the cells in series and in parallel. And you know that when two cells in your torchlight, when you combine two cells in series, say we are using one cell of 1.5 volt and another of 1.5 volt, when both are being combined together, it gives you an effect of 3 volts. Right? We will see how the cells can be combined in series first, and then later on the combination of cells in parallel, and what will be their effective EMF and the effective internal resistance. We already studied about internal resistance and the relationship of the EMF, the terminal potential difference, and the internal resistance. We will be using that to talk about the combination of cells. So let us start with the combination of the cells in series. Right? So the cells being combined in series. Let us consider two cells of EMF E1 and E2 being combined in series. So we have first cell of EMF E1, internal resistance R1, which is combined with a second cell of EMF E2 and internal resistance R2. Let this be connected to a circuit. Let me label the terminals as say A and B. Okay? The potential drop across the first cell E1, if I label this as C, potential drop across the first cell is across the points AC. The potential drop across the second cell is across the points C, B. And the total potential drop across the combination will be across A, B. So let us consider it individually. The potential drop across the first cell VAC is equal to E1 minus, I didn't mention the current, according to if it is connected in a circuit, let's say a current of I is flowing through the circuit. So E1 minus I R1. The potential drop across the second cell VCB is equal to E2 minus I R2. I hope it is understood. Now, the potential drop across a combination of the entire combination VAB will be equal to E1 minus IR1 plus E2 minus IR2, which is equal to E1 plus E2 minus I into R1 plus R2. Now, instead of the combination of cells, if we are going to replace this with an equivalent circuit, equivalent combination, which gives the same effect as having the two cells being connected in series. So let us say that the equivalent combination is this. So this terminal is A and this terminal is say B. The effective EMF is given by E equivalent and the effective internal resistance is given by R equivalent. So we know that the potential drops across the effective cell combination will be VAB is equal to E equivalent minus R equivalent. So if I call this equation as the equation 2 and the previous relation as the equation 1, if I compare these two relations, you can see that E equivalent will be equal to E1 plus E2 and R equivalent will be equal to R1 plus R2. That is, E equivalent is equal to E1 plus E2 and R equivalent is equal to R1 plus R2. Okay, I hope this is clear to you. We have combined two cells in series, and you can see that the equivalent EMF or the effective EMF is the combination, is the algebraic sum of the EMFs of the individual cells. And the effective or the equivalent internal resistance is the algebraic sum of the internal resistance of each cell. If we are going to combine two cells in a manner that the negative of the first cell is connected to the negative of the second cell, then let me just draw it down for you. We were talking about the combination of cells in series where the two cells are being combined in such a manner that the negative of the first cell is being connected to the negative of the second cell. Then in this case the effective or the equivalent EMF will be equal to E1 minus E2. That is, in the case E1 is greater than E2. The two cells, the first cell has got a name of E1, the second cell a name of E2, and the internal resistance of the first cell is R1 and that of the second cell is, say, R2. The equivalent internal resistance will be equal to R1 plus R2. Now, if we extend this result to n number of cells being combined together in series, here we have considered only two cells. N number of cells being combined in series, that is, say, a cell of E1, internal resistance R1, next another cell of EM of E2, internal resistance R2, and so on. We have a combination of n number of cells, the last cell having an EMF of En and an internal resistance of Rn. Then the equivalent EMF of the combination is given by E1 plus E2 plus so on plus En, and the equivalent internal resistance of the combination is given by R1 plus R2 plus so on plus Rn. Okay, so when we have cells being combined in series, then the equivalent EMF of the combination is an algebraic sum of the EMFs of the individual cells, and the equivalent internal resistance of the combination is an algebraic sum of the internal resistance of individual cells. Okay, now we will talk about cells in parallel. Now we have seen about the combination of cells in series. Let us talk about the combination of cells in parallel. So, talking about two cells, let us say, in parallel, if we have two cells of EMF E1 and E2 of internal resistance R1 and R2 being combined in parallel, then the circuit diagram is, this is my first cell of EMF E1, internal resistance R1, which is being combined in parallel to a second cell of EMF E2, internal resistance R2. And say this is being connected to a circuit. Let me call this terminals as A and B, and some current is flowing to the circuit. So say a current of I is flowing to the circuit. At the junction, the current I will get split up into I1 and I2. And similarly here also we have I1 and I2, which combine to form the I current which is flowing to the circuit. So, according to Kirchhoff's laws, the current directions and the current values have been written. So, you know that I is equal to I1 plus I2, where I1 is the current to the first cell and I2 is the current to the second cell. Right? Now, let us write the relations for each cell separately. The potential drop across the first cell and across the second cell will be the same as it is being combined in parallel. So let me call this junction as say C and this junction as say D. So VCD, the potential drop across the junction CD, let us say is equal to V. Now talking about the first cell, VCD equal to V equal to E1 minus I1 R1. So you can see that I1 is equal to E1 minus V by R1. Similarly, the potential drop across the second cell in this part, potential drop across the second cell, VCD equal to V is equal to E2 minus I2 R2. So I2 is equal to E2 minus V by R2. Right? Substituting these values in the relation for I is equal to I1 plus I2. Let me just rewrite this here. So we have I is equal to I1 plus I2. So I have E1 minus V by R1 plus E2 minus V by R2. Rearranging, you get E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. Now, instead of the combination of cells, if I am going to use an equivalent circuit, if I use an equivalent circuit here, right, where the equivalent circuit, equivalent combination of these two cells is having an equivalent EMF of E equivalent and an internal resistance of R equivalent and a current of I is going to flow through this. Okay, then for this cell I can write the relation V is equal to E equivalent minus I into R equivalent. Right? From the previous relation for I, we can see that V, that is, I am rearranging this equation of I is equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. I rearrange this, so I will get V is equal to E1 R2 plus E2 R1 by R1 plus R2 minus I into R1 R2 by R1 plus R2. Okay, so let me call this as equation 2 and let me call this as equation 1. So comparing the two relations, first equation and the second equation, we see that E equivalent is equal to E1 R2 plus E2 R1 by R1 plus R2, and R equivalent is equal to R1 R2 by R1 plus R2. Right? Is that understood? This is, you can see that E equivalent is equal to E1 R2 plus E2 R1 by R1 plus R2, and R equivalent is equal to R1 R2 by R1 plus R2. Okay, putting this in a more simpler form, we have E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2, and R equivalent is equal to R1 R2 by R1 plus R2. If you extend the relation to n number of cells which are being combined in parallel, then the relation for n number of cells is n number of cells in parallel. Then we have E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2 plus so on plus En by Rn, and 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus so on plus 1 by Rn. Okay, this is a relation for n number of cells being combined together in parallel. So I hope children you understood what is the combination of cells and how we can combine the cells in series and parallel, and what will be the effective EMF and the effective internal resistance that is being produced. And in different combinations that we use in daily life, you should be able to analyze this. Okay, thank you.